friends, now I want to carry on with Unit 2. Unit 2 has got to do with giant covalent structures. It's Unit 10, sorry. Yeah, Unit 10. Let's close up here and see if I've got Unit 10. Okay, Unit 10. It is about giant covalent structures. Now, before we start with this, I want to explain something. Let's just add in a page. All right, people, when we have covalent bonds, the product of a covalent bond is a molecule. Okay, and examples of these molecules are things like water, methane, CO2, NH3. They are, relatively speaking, small molecules. All right, so we just refer to them as molecules. But sometimes a molecule forms a very large structure. Now, we've done a little bit on diamonds and graphite. I said to you, I think, in diamonds, carbon has 4 bonding places. So in diamonds, each of those 4 bonding places are bonded onto 4 carbons. Okay, now, people, we differentiate between, when we have covalent bonds, we differentiate between molecules and macromolecules. The word macro refers to very large. Okay. We basically get 2 types of macromolecules. The one is the giant covalent, and the other one is a so-called polymer. Now, polymers, we won't do much with them at this point. When we do organic chemistry, we will have a look at the polymers. Okay? Maybe when we do a little bit on the chapter on materials, they will refer to the polymers. This module, this Unit 10, has got to do with these giant covalent structures. Okay, and the examples that we are going to have a look at are diamonds, graphite, and silicon dioxide. All right, so people, you have to differentiate between these two. In normal molecules, it's 2 or 3 or 4 or maybe 5 atoms in that molecule. Macromolecules have got thousands sometimes, especially the giant covalent structures of atoms covalently bonded to form a giant covalent structure. Now, normally, what are the properties of molecules? Yes, soft solids, otherwise they are liquids or gases. They have low melting and boiling points, and they are poor or no conductors. Are you with me? These giant covalent molecules, would they have the same properties? Definitely not. Because remember, between these molecules, one water molecule and another water molecule, what forces are there? Very weak forces, van der Waals forces. Alright? But if I have a giant covalent structure like diamonds, where each carbon is bonded onto 4 others and they are bonded covalently onto 4 others, if I want to break that structure, what must I break? I must break the chemical bond. So, we find that macromolecules are usually very hard substances. They have usually got much higher melting and boiling points, and their electrical conductivity will differ, as we will see in the examples that we will do. Alright, so keep that in mind when we work with molecules. Diamonds are molecules, but diamonds are very hard and very strong. They have very high melting and boiling points. Okay. The electrical conductivity differs. Diamonds don't, but graphite does. Okay, so let's have a look. They say giant covalent structures. Remember, giant covalent are macromolecules. Macromolecules can be polymers. Yes, polymers are long chain-like molecules. Your hair is a polymer. The cellulose fiber in the desk is a polymer. Long chain-like molecules. Yes. Okay. So macromolecules, then polymers and giant covalent structures. All right. So giant structures, very large molecules, thousands of atoms bonded covalently in 3 dimensions. All of them large 3-dimensional structures. The atoms are held together by covalent bonds. So if you want to break them apart, you must break the bond. It will require a lot of energy. And they are joined together to form giant covalent structures. They form part of the group of molecules known as macromolecules. Macro, large. All right. Macromolecules can be divided into 2 types, giant covalent and the polymers. Now, we are looking at the giant covalent. The polymers we'll do later on. Allotropes. What are allotropes? We've done that one. Different crystalline structures for the same element. Normally, if I have an element, it will form a specific crystalline structure, and I can use that structure to identify the substance. Now, some elements have more than one type of crystalline structure. It depends a little bit on the conditions under which they were formed. Diamonds prefer high pressure, high temperature. Graphite is formed under different conditions. So, allotropes, different crystal lattices for the same element. The first allotrope of carbon. The first one, diamonds. The second one, yes, and there is a third one, buckyballs or Buckminister Fullerene. Okay. In diamonds, each carbon is bonded onto 4 others. Remember, carbon is actually a very, very unique element because it has 4 bonding places. It's lots of bonding places. Okay? So, to form diamonds, each carbon is bonded covalently onto 4 others, and those 4 are bonded covalently via 4 covalent bonds onto 4 others, forming a giant covalent structure. In diamonds, the carbon atoms are held together by covalent bonds. What do we know about covalent bonds? They are strong, difficult to break, and not intermolecular forces. That's why I can pour water, the molecules can slide over each other, because the forces holding them together are weak. I can't pour diamonds. In actual fact, it's very hard or difficult to break a diamond, because the carbons are held by covalent bonds. The formula for a diamond is just very simply C. C for carbon. Because if you have a big diamond, you'll have more carbon atoms, and if you have a small diamond, you have less carbon atoms. But in diamonds, the carbon atoms are bonded covalently in 3 dimensions onto 4 others, and they in turn onto 4 others. Okay, so there isn't a specific formula. I can't say, like with the Buckminister, C60. Are you with me? It's just C because they are, well, C, if you wanted to, you can put a footnote in any natural number, counting number, okay, not naught. Chemical bonds are much stronger than intermolecular forces, so they are difficult to break, and therefore diamonds have high melting and boiling points. In actual fact, diamonds tend to undergo sublimation at very high temperatures. If there is no oxygen available, the carbons will maybe break apart and it will form carbons in the gaseous state. But they very easily condense, and if they condense just under normal atmospheric pressure, it will form soot. The black stuff, if something burns, is carbon. Okay, so diamonds undergo sublimation at very high temperatures, about 3,900. They will melt at extremely high pressures. They will melt. Are the forces between the separate carbons very strong once they're broken apart? No. So they want to actually sublimate and form carbon in the gaseous state. How can I convert a gas to a liquid? By compressing it. You understand? That is very hot. And there are diamonds in that fire. They usually react with oxygen in the air and they form carbon dioxide. They burn away. But it has to be very high temperatures. So at very high pressures you will get diamonds to melt. When diamonds are heated in the air, they start reacting with the oxygen and they form carbon dioxide, which is a gas, and it will just dissipate into the air. And you'll have nothing left, yes, of your $15,000 or $25,000 diamond. Now normal fires, it could reach that temperature, but there would probably have to be something that likes burning. A good combustible fuel, yes, something like that. Okay. Now back to the structure. In the structure of diamonds, each carbon has 4 bonding places, and they are filled by means of covalent bonds onto other carbons. There are no free electrons. Why am I interested in the free electrons? Whether it can conduct or not. If there are no free electrons, can it conduct? Nope. So will diamonds conduct? No. All right. So diamonds do not conduct electricity. Where do we use them? Because they are extremely hard. We use them for cutting and drill bits. Very hard points that don't need to be sharpened all that often. It's usually the lower grade. They talk about industrial grade diamonds. What do we do with the other diamonds? Yes, we make jewelry. Why do we make jewelry? Because they tend to have a very high refractive index, so when light shines on them, they sparkle. They do have flaws in them. The pattern is disrupted, and I think sometimes the white diamonds are probably more pure than what a yellow diamond would be, or something like that. Okay, yeah, it's got to do with other substances that also get trapped in that bond. All right, now, graphite. Graphite is the other allotrope of carbon that we have to have a look at. And graphite is actually very interesting because carbon has got 4 bonding places. In graphite, each carbon only bonds onto 3 others. If you look at this carbon over there, it forms 1, 2, 3 bonds. You can take any one. Look at that one, it forms 1, 2, 3 bonds. Look at that one, it forms 1, 2, 3 bonds. Buckminister Fullerene forms a ball. So in that way they are similar. But graphite doesn't form a ball. It forms flat sheets having this structure, in the 2 sheets together. What would hold this layer onto that layer? What force do we get between molecules? Weak van der Waals forces. That is why graphite is used as a lubricant, because that layer can slide off the next layer. And there are billions of layers in graphite, all right, on molecular level. So we use graphite as a lubricant. All right, so it's flat sheets that can slide off each other. Yes, that's why when you rub it, it's slippery. That's why when you write with your pencil lead, a layer rubs off and is left on your book, and it's just from the force of the friction between your books. Yes. Okay. So graphite, the molecules are not held together as strongly as in diamonds, because in diamonds, one carbon is bonded covalently onto others. To break a ring-like structure apart is going to require a lot of energy, because there you must break chemical bonds. But to separate one layer from another is very easy, because it's weak van der Waals forces holding the layers together. Okay, so graphite will also have a high melting point because it's difficult to break covalent bonds. Okay, if you want separate carbon atoms. So a high melting point. It also tends to undergo sublimation. And it will only melt at very high pressures, just like diamonds. Do you understand? 4,000 Kelvin and 100 atmospheres, 100 times atmospheric pressure. the separate layers of graphite. In other words, that layer and that layer are held by weak van der Waals forces. So, the layers can slip off each other. They can easily slide off each other. Therefore, graphite, in that sense, is soft and flaky. But the soft and flakiness refers to the layers sliding off. It does not refer to breaking up a layer. Alright. Because it's soft and flaky, the layers can slide off. We use graphite as a lubricant, especially in locks, where if you put in oil, the dust goes in and it clogs it eventually again. With graphite, it won't attract the dust, and it will allow the tumblers to slide as they should. Or in a pencil, lead. Just go back. Diamonds, a graphite, will they conduct electricity? Yes, because each carbon is bonded onto 3 others. So on each carbon there's 1 electron that's not held in a chemical bond. And that electron is free to carry charge. So that electron will allow graphite to conduct electricity. Do other molecules conduct electricity? No, but remember we're busy with macromolecule. The third macromolecule that we must have a look at is silicon dioxide. Now I don't have a picture of silicon dioxide. I think in your textbooks there is a picture. If you go and have a look at silicon dioxide, you will see they say silicon exists mainly in the form of silicon dioxide. Look at the formula. It is silicon 4 oxide. Silicon 4 oxide. What does the 4 refer to? Where would you find silicon? Below carbon, how many bonding places? 4. Alright? So, yes, in its simplest form, 2 to 1. So, SiO2 is the formula for silicon dioxide. It's found in quartz and sand. We find that each silicon atom is bonded onto 4 oxygen atoms. Okay? How many bonding places does oxygen have? 2. So each oxygen is going to be bonded onto 2 separate silicons. Do you understand? Yes, it makes it very strong. So we have a large covalent structure molecule. It will have a high melting and boiling point. It will be a very hard, solid. Will it conduct electricity? Confuse it over there is silicon itself is a semi-conducting material. So probably, I'm not perfectly sure whether silicon dioxide does conduct or does not. So high melting and boiling point, and if you want to break it, you have to break covalent bonds. So, properties of diamonds and silicon dioxide, why do they put them together? How would graphite differ? Graphite is soft and flaky, and graphite will conduct electricity. Okay. session, we had a look at the different shapes that molecules can have. And we said, just very basically, just to recap, we said that the covalent compounds can be divided up into specific shapes depending on how many bonding pairs of electrons and how many lone pairs there are on the center atom. We then said that single pair repulsion is the strongest, bonding pair is the weakest. Alright, and we found then that molecules can be pushed into specific shapes. Carbon dioxide forms a straight line. We say that molecule is linear. Alright, most of the covalent compounds that consist of two atoms will be linear. Then we said water. Can anyone remember the angle that there was between the hydrogen, oxygen, hydrogen on the water? I think it was 107 or 104.5. Okay, we'll have a look at them in a moment. But we said then the water molecule is V-shaped. Ammonia, NH3, is pyramidal, and methane is tetrahedral. Now we are going to have a look at them as we do in theory. Okay. Now, what is important is that carbon forms the center atom. We have two bonding pairs there, two bonding pairs there, two single pairs, two single pairs. We will find that the repulsion on both sides of the center atom is the same. All right, and it will push the angle between the oxygen, carbon, oxygen into a straight line there. All right. So the repulsion of the oxygen atoms is the same. Therefore, the bond angle is 180 degrees, forming a linear shape. Very important, the name of the shape. Then from that, we can go and have a look at the water. We see here that the oxygen has got two single pairs which repel each other strongly in 3 dimensions as far away as possible. Then we have a bonding pair over here, bonding pair. So the repulsion between bonding pairs and single pairs is also fairly strong, but not as strong as between the single pairs only. So that also pushes the hydrogen atoms away downwards to one side. The repulsion between this bonding pair and that bonding pair is very weak, so they can't repel each other very strongly. And as a result of that, we find that the bond angle over here is going to be 104.5 degrees. Now you need to remember the size of the angle. Okay, they won't ask you obscure examples, but you need to know carbon dioxide, water, ammonia, and methane. All right, it's just basic classical, or the classic examples for V-shaped, pyramidal, tetrahedral. Okay, so water then is 104.5 degrees, the bond angle. The next molecule that we have to have a look at is the ammonia molecule. Remember, it's NH3. So in the ammonia molecule, we have got 3 bonding pairs that repel each other fairly weakly. All right? So the repulsion over here and over there is not very strong. And, well, over there, remember, it's 3-dimensional. It's not very strong. We only have one single pair over here. So we don't have single pair repulsion like we had in water. Alright? We've only got single pair, bonding pair repulsion, and bonding pair. That is why we find that the bond angle in the ammonia molecule over there, that angle, is slightly bigger than in water, because the forces pushing those hydrogens down to one side are slightly weaker. So the angle over here is 107 degrees. Same over there as well, 107 degrees. All right. Okay. The last one, we call the shape then of the ammonia molecule, where we have a single atom over here and 3 on the bottom, forming a triangular base. We call that triangular pyramidal or just pyramidal. All right. There we go. Is a pyramidal shape. Then methane is probably the easiest one to explain of the lot. Are there any single pairs of electrons? No. We have 4 sets of bonding pairs. There's one set, there's another set, and another set. And we find now that the repulsion between these pairs are fairly weak, but it is the same in 3 dimensions. There's not a force pushing it stronger from one side of that molecule. So these carbon-hydrogen, the hydrogen-carbon-hydrogen angles will all be the same size, and they will be as far away as possible that they can get in 3 dimensions, forming an angle of 109.5. So, try and remember it. Water, 104.5. What was ammonia? 107. And the last one that we've done now, 109.5. So 4, 5, 6, 7, 7, 8, 9. Okay. Try and get yourself a system to remember the size of the bond angle. If you can remember the sizes, you would be able to figure out which size belongs to which atom. Why is the bond angle in water smaller than in methane or ammonia? Because in water, we have got single pair repulsion that pushes the hydrogen atoms down. You follow? All right. Why is the angle in ammonia bigger than the angle in methane? Methane only has bonding pairs which repel each other equally weak in all directions, while in the ammonia molecule there is one single pair that repels the bonding pairs fairly strongly away. All right. So you need to try and remember the size of the bond angle. Okay, people, now we've had a look at ionic bonding. We've had a look at covalent bonding. Now we're going to compare the properties of ionic compounds and covalent compounds. Now the physical properties of these compounds have got to do with the strength of the forces between the particles. What makes it sometimes difficult to understand, if we have an ionic compound, we have a crystal lattice that consists of positive and negative particles, and you can all understand that opposite charges attract. So we said then that in an ionic compound, the forces over here between the particles, what are the particles? Ions. What forces do we have between ions? Are Coulomb forces. Okay, the Coulomb forces are fairly strong. All right. Now, when we're going to have a look at molecules, it's slightly different. A water molecule, for argument's sake, will have that shape. So here is the whole water molecule. Within the molecule over there, we have a covalent bond. It's a chemical bond. But if I have 2 water molecules, what forces exist there? Those are weak. Van der Waals forces. All right. Between molecules, we have weak forces. Between ions, we have the ionic bond. It's a chemical bond. It's strong. Alright, no matter how big my salt crystal is, whether I have one as big as a grain of sand, or I have one as big as a block that I go and put out for the kudus to lick near the water, okay? The salt crystal is held together by ionic forces, electrostatic forces between ions. It's a strong chemical bond. But with molecules we differentiate. We talk about intermolecular between two molecules. The inter-Cape bus travels between Cape Town and Windhoek, the inter-Cape. But within the molecule over there, those forces there, let's do them in a different color. Those forces, that is an intramolecular force. It's a force inside the molecule, and that happens to be a covalent bond, which is strong. Covalent bonds are strong like any other chemical bond is strong. But I think what confuses you eventually is the fact that when we work with ions, it's easy to understand. The forces between the particles are just Coulomb forces, forces between charged particles. But when we start working with molecules, we have to differentiate two types of forces. The chemical bond within the molecule. And that one does not determine melting and boiling point. Okay? The forces between the molecules are the ones that determine melting and boiling. You need to understand this concept very clearly. My fingers are bonded onto my hand. Okay? I can't break off a finger very easy. That's like the forces inside the molecule. But my two hands can be held together by weak van der Waals forces. Alright, an image. Okay, so it's not within the molecule. It's between the molecules. Alright, and from that we can differentiate specific physical properties. People, ionic compounds, we've done this in previous years. What are the properties of ionic compounds? They are all solids and they are all hard and brittle. So if you hit them with a hammer, they will shatter. Alright, why are they hard and brittle? We have strong forces between the particles. If there are strong forces between the particles and I want to try and make that solid melt, I'm going to need lots of energy to give the particles enough energy to vibrate far away from each other to overcome the forces. So we find then that ionic compounds have high melting and boiling points. People, they are really high, 900 degrees, 950, 2015 degrees. Okay? They have very high melting and boiling points. The reason being strong electrostatic or Coulomb forces between the particles. Ionic compounds, they can conduct electricity, but not in the solid state. Because why? In the solid state, the charged particles are held fixed in a crystal lattice. Alright, to be able to conduct electricity, the charges must be able to move. So when I melt a salt, or when I dissolve a salt in water or any other liquid that it dissolves in, we will find then it will conduct. Alright. The reason why water conducts electricity, the water coming out of the tap, is there are salts dissolved in the water. So it's actually not the water that conducts, it is the dissolved salts that are the charges that can move. And the moment you have moving charge, you've got electricity, current. No? Pure water won't conduct, it's molecular. Alright, so it will conduct in the melted or dissolved state, and it's important to state that. Okay, because later on when we do the metallic bond, metals will conduct whether they are melted or whether they are solid. Okay, so you must distinguish. They will conduct when the salt is melted or dissolved. It does not conduct when it's in the solid state, because the charged particles are held in a crystal lattice. Okay. Covalent compounds. remember, the forces between the particles are weak. So, if they are solids, they will be soft. Mothballs, for example, are molecular solids. What happens to mothballs if I leave them on the shelf, open outside of the packet? Doesn't dissolve? What's the process called? Doesn't evaporate? Yes, it undergoes sublimation. It goes from the solid state directly to the gaseous state. Why doesn't it go to the liquid state? The forces holding those particles together are so weak that the moment the particles get enough energy, they can go and become a gas. Alright, so if they are solids, they are soft solids. Usually we will find that any of the covalent compounds that we work with are liquids, or, there's a typing error, or gases. People, if we look at things like HCl, HCl is actually a gas. We work with it as hydrochloric acid, but that's the gas dissolved in water. That is why when I open up the bottle of HCl, it immediately starts giving off fumes. Ammonia is another one, NH3, is actually a gas at room temperature. It dissolves in water. So I can add it to Handy Andy to help clean up fatty deposits, etc. But when you work with Handy Andy, you immediately smell the ammonia because it wants to become a gas again. Things like hydrogen sulfide is a gas. Carbon dioxide, CO2. The only one I think that you really work with that is a liquid, or not even work with, but that you know of, is bromine, diatomic molecule. It's a liquid. Iodine is a solid. But iodine, just like mothballs, if I have a crystal of iodine and I start heating it, it doesn't melt, it immediately becomes the gas. Alright, so the forces between those particles are very weak. That is why most of them are in the form of a gas. The ones that are liquid would be my organic compounds, because the molecule gets a little bit bigger and a little bit heavier. Okay, and then they require a little bit more energy to make them evaporate. So things like ethanol is a liquid, methanol is a liquid. Okay, carboxylic acid is a liquid. Okay, those ones then, but we won't work with them at this point. When we do organic chemistry, we will work with those ones. Alright, so they, because of the weak forces, they will have low melting and boiling points. You understand that? Requires very little energy to be added so that the particles can overcome the attractive forces. They use the term low volatility. In other words, they will evaporate very easily. Okay. Low boiling point goes together with low volatility. It simply means it will evaporate very easily. For example, if I have diesel in a puddle and I've got petrol in a puddle, the diesel is going to take longer to evaporate than the petrol. Okay, petrol is more volatile than the diesel. They do not conduct electricity. Okay, why don't they conduct electricity? What is electricity? Current. Moving charge. Are there any charges that can move? No. Alright. So there are no charged particles, so it cannot conduct electricity. And the last one, mostly not soluble in water, while the ionic compounds are mostly soluble in water. Now this last one, there are quite a few exceptions to the rule. In general, in chemistry, we say, like dissolves like. Something will dissolve another substance if the forces between the particles are more or less the same size. Does that make sense? Because if the forces between, let's say I've got a liquid, and the forces between the liquid particles are very strong, and I'm trying to make a solid substance dissolve in it, if the forces between the solid substance is not strong as well, they can't move in between each other. Alright, so like dissolves like, there are a couple of exceptions. Normally, for example, if I take sugar and salt, if I take petrol Petrol is a molecular substance. It's a hydrocarbon. Sugar is also a hydrocarbon. Sugar can dissolve in petrol. If I took normal table salt is ionic. Table salt does not dissolve in petrol. Why? The forces between the salt particles are much stronger than the forces between the petrol particles. Do you understand that? Now water messes us around. Water is actually a very, very special compound, and you've done that last year already where we said we look at the melting point of ice and what happens to, why does ice float on water? Because it expands between 4 and 0 degrees. Okay, now water, because of its very special shape that it has, and because of the 2 single pairs of electrons that don't form a bond, we find that the water molecules, the forces between them, the water molecule is almost, it isn't an ion, but it's almost an ion. Okay, it's got a slightly negative side and a slightly positive side. We'll have a look at that later on as well. So we find that water can sometimes dissolve molecular substances, and other times it can dissolve ionic substances. For example, if I add water to petrol, will they dissolve? No. But if I add sugar to water, will it dissolve? Yes. Do you understand? Okay, so there are many exceptions, but just as a general rule, like dissolves like. Right. Okay, so those then are the properties of ionic compounds and covalent, just very general properties. Now, the next term that we have to have a look at is something called an allotrope. Nice new definition. Have you done allotropes before? Nope, you've not. So allotropes, they are different crystalline structures for the same element. And a very, very well-known example is diamond and graphite. They are both made out of carbon. But we get 2 different crystalline forms. They are formed under different conditions. Diamonds are formed under very high pressure and very high temperatures. Alright? Usually in the columns of volcanoes with a molten rock and organic matter that is burning, alright, and sublimating. When it cools down and there's no oxygen present, then we can get the formation of diamonds. Graphite is formed under different conditions. Graphite is the stuff they put in your pencil lead. If you have a lock that sticks, you buy graphite powder and you puff a little bit of graphite powder into the lock. It acts as a lubricant. Okay? Both are made out of carbon. Now, we will go into the specific shapes of diamond and graphite in one of the next units. Right? So, there's a third allotrope for carbon, one that is called Buckminister Fullerene, or just very simply shortened down to Bucky balls. Okay. The Buckminister Fullerene consists of 60 carbons covalently bonded onto each other in structures that look like a soccer ball. You follow? The patches on a soccer ball? Okay, 8-sided. Buckminister Fullerene look like a soccer ball. So it's a hollow ball of carbon. Alright. We will go and look at materials that are made with them and things in one of the next topics. I don't want to start with that now. Just a little bit more about Buckminister Fullerene, or just Bucky. They will accept both. It shouldn't be a problem. They sometimes refer to them as fullerenes as well. They are homonuclear. What does that mean? Homonuclear. The same nucleus. What is heteronuclear? Different nuclei. In other words, bromine is homonuclear, diatomic, same bromine and bromine. But HCl is heteronuclear, a hydrogen and a chlorine. Okay, so Buckminister Fullerene are homonuclear because they consist of carbon atoms, identical carbon atoms. They can be spherical, okay? That's their natural form, the buckyballs. And we can open them up and we can build them into structures like tubes, which we will go and have a look when we do different materials. And this is where we get the carbon fiber materials, etc., that are very strong, and so on. The spherical fullerene contains 60 carbons and are called Buckminister Fullerene, or buckyballs, while the tube fullerenes are known as nanotubes. Where have you heard about nanotubes? They're investigating nanotubes in terms of conductivity, because graphite conducts, and the nanotubes are made from the fullerene, that they tend to, make them build onto each other to form long tubes. And these tubes can conduct electricity. There is less resistance in a nanotube than there is in a copper wire. Alright, so in terms of, yes, at this point it is expensive. Alright, but it's where the new research is going into. Okay, fullerenes are used as drug delivery systems to the body, lubricants, and catalysts. Now we'll have a look at that when we get there at this point. There's a check your progress, page 135, that you have to do for me for homework. All right?
We're talking about COVID. Babaji, tell us about the day you found out you had COVID.
The day I found out I had COVID. It was a difficult day. I didn't understand how I got COVID, because I was always covered, I was always with my hand sanitizer. It came with my wife. And that whole day, I was thinking, what's gonna happen to me? I'm gonna survive. My kids, I was losing my tasting, smelling. There were some days I will test my taste buds and put like 4 or 5 chilies in my coffee. No ways. I didn't taste it.
So did you also lose your appetite in the process?
It was very funny. In the first week, no, I was chowing. I was chowing like, I will wake up like midnight and make for me something. But after the first week, then the appetite was gone. When you go to bed, your body is also automatically switching off. And that's a dangerous time for COVID. It's like glass pinching you, cutting you inside your lungs. Then the heart was pumping like rubber pumps. You are losing a lot of fluids at night.
Is that through fever or what?
Yeah, it's through fever.
So have you experienced any side effects from having contracted COVID-19?
No, not yet. Maybe still coming, but not yet.
And your wife?
She was complaining about light head. It's an annoying headache. It's light, but it's annoying.
So basically you didn't take any prescribed medicine from the doctor to recover from COVID?
No, I didn't. The only thing I was using is desperate for my blood not to clot. Because for some people, when your lungs are really, really infected, your blood will start to clot from the lungs, close all the airways. That's where we are passing. I'm smoking cigarette, and when you were a smoker and COVID in your lungs now.
So then after you both found out you had COVID, what did you guys do to protect the kids?
The kids move out from the house. The Buddhists will come, then we'll collect everything for them and just put for them outside. When they came, just grab the food and go.
So what was the biggest battle for you? Was it mental or physical?
Mentally. Mentally was the biggest battle. I'm actually an international movie maker, and my career was cut off. I couldn't put bread on the table. There were some days you have one meal for the day, then went to bed. And that was hitting me in my mind. What if Blessing gets corona now? Where am I gonna go? Who's gonna help? There were also some people depend on us in the rural areas. We couldn't help them. My future was black, dark, dark, dark. I couldn't even see that small light at the end of the tunnel. One day, my daughter decided, now, I want to see my father today. And I just told her, yeah, she can come. The first words was, Daddy, I was praying for you yesterday night. Don't worry, Corona will go back soon. And I was asking, from where? From Namibia? She said, no, not from Namibia, from you. And you are not looking good. And she was actually heartbroken. Until today, she hates Corona. From there, then I was like, oh, okay. If the smallest one is saying this, why am I not picking me up self and do the right thing and get rid of this thing? That's where I started to run, to practice, coming to my quiet place. And actually, the main thing that broke my heart during that time was there was no one. The time of COVID, there was no one.
So can you tell us where we are right now?
We are at my silent place. I call this place my silent place. I will come here when the COVID is hitting me like 120%. Looking at the ocean, then you will hear voices like, no, you don't belong here. Today, you don't belong here. Get up and go home. Some days, they will nurse you like, no, you will survive. Your future is a bright future. You must not give up now. Think about your kids. Think about the people around you. Even the wind will do that. Actually, you must meditate. The thing of COVID is, looks like COVID is afraid of the warmness and is friends with the coldness. So the whole time you are baking in the sun, it helps a lot.
So is that what you did?
Yeah, I did. I will do that twice a day. This was supposed to be a golden year for me, a very, very good golden year for me, but then COVID decided now, this is not going to be your golden year. Everything was cancelled. We, the filmmakers, this year, from the international shoots, lost lot of money.
You've lost 3 family members? Is it all due to COVID?
No, not all due to COVID. First one, my sister. She was very close to me. She contracted COVID April, and she was in ICU for 3 months. The COVID damaged her lungs, and at the stage her lungs collapsed and she couldn't breathe without the machines. Her kidneys failed, her liver has failed. COVID is real. First of all, COVID is real. It's not a joke. Most of the people, they fall away from COVID regulations. Still early to fall away from COVID regulations. We must still go in line with those COVID regulations.
And how long did you say it took you to recover?
3 weeks, 21 days.
What must somebody do to change your mind from that negative perspective to that positive?
COVID, no job, it's very dangerous. There was one day I just decided I'm gonna take a rope, go to the jetty, sit around there, and after all I will hang there by the jetty. The time I arrived here there was no wind, out of nowhere. The ocean was like angry, and it started to get cold, and I was like, but it was just nice weather. Then I sat down. Then the universe will talk with you, the wind, the sun, the ocean. That's the main thing of COVID. If you don't save yourself, no one will save you. And we must always appreciate what we have around us. That's the main thing in COVID. If you don't appreciate what you have around you, no, you will lose your head.
Smile, smile, smile. When you walk with me, I just want you to smile, smile.
My industry and what I've done with my hands in Namibia, it's going all over the world, and here you are, Papa G, you want to quit? Now, I'm excited for 2021. It's not gonna be the same like 2020 now. I'm getting back in the groove.
Give me food, clothes, water, and shelter. Nothing else, no matter. You're my moonlight in my oven. Let all my sins be forgiven. Happiness rain on me. Never let the children cry. Namibia, smile.